There's this specific kind of magic that we all interact with, probably 20, maybe 30 times a day, and we don't even think about it.
Only 20. I think you might be underestimating it.
Fair point. I'm talking about that moment, right? You walk into a coffee shop, you open your laptop, or maybe you're plugging a cable into a server rack.
Yeah.
You plug it in, you see that little spinning circle for just a fraction of a second, and then, boom, you're connected.
It feels instant.
Yeah.
And, I mean, ideally, it should feel instant.
Exactly. But the more I looked into the research for today's deep dive, the more I realized instant is a massive oversimplification.
Yeah.
There's this frantic, invisible negotiation happening in that millisecond.
It's a whole conversation, a really sophisticated one.
Right. It's not just a device waking up. It's a full-on dialogue between your machine and the network.
It really is. And specifically in the world of IPv6, which is what we're unpacking today, that conversation is it's radically different from the old IPv4 days. It's more autonomous, more complex, and frankly, a lot more elegant.
And that's our mission for this deep dive. We're getting into that dynamic negotiation. We've got a stack of technical diagrams, command references, all this material that explains exactly how an IPv6 device gets its identity. We're talking SLAAC, DHCPv6, router advertisements.
And the mystery of the flags.
Yes, the flag.
And honestly, if you can grasp this one handshake we're about to discuss, you basically understand the core philosophy of modern networking. It's this constant tug of war between autonomy, letting the device figure things out, and control, telling the device exactly what to do.
Okay, so let's jump right into the source material then. There was a concept that just immediately jumped out at me. It's almost philosophical. It's this idea of existence precedes connectivity.
Right. This is the first big aha moment for anyone coming from IPv4. In the old world, if a DHCP server didn't hand you an address, you were basically a ghost. You couldn't talk to anyone.
You just didn't exist on the network.
Exactly. But in IPv6, you have an identity the second you power on. Before you even look for a router, your device gives itself what's called a link local address, an LLA.
The one that starts with V80. If you open your command prompt, you'll see it right there.
You will. And the source material had a great analogy for this, the office building intercom.
Yeah, I like that one.
Think of that link local address, that V80 address, as the internal intercom. You can talk to anyone else in that building on your local subnet. You can ping them, share files. You have existence. You are a real entity in that room.
But you can't make an outside call. You can't order a pizza.
No.
No.
Pizza, you have no outside line. That V80 address is strictly non-routable. It dies the second it tries to cross a router. To get to Google or Netflix, you need a global unicast address, a GUA.
Which is usually that 2001 address we see.
Correct. That's your public phone number. And the whole point of this deep dive is to figure out how you get it. How do you go from the intercom to the global telephone network?
Okay, so let's set the scene. My laptop is on. I have my V80 link local address. I'm on the intercom. How do I find the way out? How do I even find the router?
You have to ask.
Yeah.
But, and this is a really crucial difference, you don't shout.
Not like IPv4, where you just broadcast to everybody.
Exactly. That was so noisy. IPv4 was like yelling, hey, I need an IP, and every single device had to stop and listen. In IPv6, it's way more polite. Your device sends a quiet little message called a router solicitation, an RS.
Which is basically just anybody out there, any routers.
Pretty much. But it sends it to a very specific multicast address, FS02.2, that literally means all routers. It's like whispering on a radio frequency that only routers are listening to.
So the printers and the other laptops, they just ignore it.
They don't even hear it. It's incredibly efficient.
So the router hears this little whisper. What's its response?
It replies with a router advertisement, or RA. Now, routers are actually pretty chatty. They send these out periodically anyway, maybe every 200 seconds. But if it hears a solicitation, it replies immediately.
And that advertisement goes to everyone.
This one does, yes. It goes to FS02.1, which means all nodes. So the router basically steps into the middle of the room and makes an announcement. It says, hi, I'm the gateway. Here's the network prefix. And crucially, it also says, and here are the rules of engagement.
This is where it gets really interesting for me. The rules of engagement. They aren't just a manual. They're basically a set of binary flags. The diagrams in our note, they look like tiny little switches on a circuit board.
That's the perfect way to think about it. Inside that RA packet are 3 specific bits, 3 little switches that tell your device exactly how to get online. The A flag, the O flag, and the M flag.
So it's a logic puzzle, and depending on which switches are on or off, my laptop takes a completely different path.
Exactly right. The host reads the flags, runs the logic, and decides its own fate.
Okay, let's break down those flags before we hit the paths. The A flag.
A is for address auto configuration. If that switch is on and set to 1, the router is telling your device, I'm giving you the first half of the address, the prefix, but you need to figure out the second half yourself using SLAC.
SLAC, stateless address auto configuration. It sounds like a comic book word.
It does, but it just means do it yourself. The router is basically saying, you're a smart device, you handle it.
Okay, what about the O flag?
O is for other. This covers everything else. An IP address isn't enough. You need DNS servers, maybe a domain name. If the O flag is on, the router is saying, you can handle your own IP, but go check with the server for the other details.
And the last one, the M flag, the big one.
M for managed. This is the control freak switch. If M is on, the router is saying, stop, do not make your own address. Go ask the stateful server for everything. Full administrative control.
So those three switches, A, O, and M, create three distinct paths. Let's walk through them. Path 1. The source material calls it SLAC only.
This is the most common one you'll see on simple networks. If you're listening at home on Wi-Fi, this is almost certainly what you're using. The flag configuration is A equals 1, O equals 0, M equals 0.
So autoconfig is on, everything else is off, the total DIY approach.
It is. The router sends the prefix. So the first 64 bits, let's say it's 2001.dba.akid.1. It just hands that over and says, here's the neighborhood. You pick your own house number.
And that house number is the interface ID, the last 64 bits.
Correct. So your device takes the prefix, generates its own interface ID, and just smashes them together to make a full 128-bit address.
Okay, I want to pause here for a second because there's a detail that really surprised me. In this DIY scenario, where does the default gateway address come from? If there's no server handing out settings, how do I know where to send my traffic?
That is a fantastic question, and it loops all the way back to the beginning. Remember the link local address? The fee 80 one?
The intercom number.
Yes. The router sends that router advertisement using its own link local address as the source. Your laptop sees that message come in and basically thinks, oh, the device that sent me these rules, that fee 80 address, that must be my way out. That's my default gateway.
Wow. So my global internet traffic actually gets sent to the router's local intercom number first.
Exactly. You don't need a global address to find the gateway, just the local one. It's incredibly elegant.
Okay, so the DIY part. Generating that interface ID. The notes say there are two main ways to do it. One is hardware-based. The other is, well, random. Let's start with the hardware one, EUI64.
Right. This is the classic method, though it's kind of falling out of favor now for privacy reasons. EUI64 is deterministic. It takes your network card's 48-bit MAS address, its unique serial number, splits it down the middle, and jams FFFE right in the center.
It just injects FFFE.
Yep. To pan it out to 64 bits. And then it does one more super nerdy thing that network engineers love. It flips the 7th bit.
The 7th bit, why?
It's called the universal local bit. Flipping it is just a way to signal that this address is globally unique. The point is, it's a mathematical process. If I know your MNASI address, I can predict your IPv6 address.
Which sounds great for an admin, but a little creepy for a user.
Well, yeah, that's the privacy issue. Think about it. If you take your laptop from home to a coffee shop to an airport, the first half of your IP, the prefix changes every time.
Yeah.
But the second half, the part made from your hardware, stays exactly the same.
So someone could track me. They could see that this specific interface ID was at my house, then Starbucks, then the airport. They could map my movements.
Precisely. You're carrying a digital license plate. And that is why modern systems, Windows 10 and up, pretty much all mobile phones, they default to the second method. Random generation.
Rolling the dice.
Literally. They just generate a random string of hexadecimal characters for the interface ID. It changes when you connect to a new network, so it breaks that tracking.
Okay, that makes sense. So whether I use my MSC or a random number, I've built my own IP. But what if someone else in the network randomly picks the same number as me?
A collision. Yeah.
Right. In the old days, a central server would prevent that. Here, we're just hoping for the best.
Well, not just hoping. There's a process for that. It's called deduplicate address detection.
Trust but verify.
Exactly.
Yeah.
Before your device actually commits to using that new address, it sends out another little whisper, a neighbor solicitation. It's basically asking the room, hey, is anyone else using this exact address?
It's like pointing at an empty seat in a movie theater and asking, is this one taken?
Perfect analogy.
Yeah.
If someone is already using it, they send back a neighbor advertisement that says, yes, it's taken, and your device has to try again.
Yeah.
But 99.9% of the time, there's just silence.
And silence is good.
Silence means the address is unique. You claim it, and you're online.
Okay, so that's path 1, SLAC only, independent DIY. Let's talk path 2, stateless DHCPv6, the hybrid approach.
This is where we start to mix and match.
Yeah.
The flags here are A1, O1, and M0.
So A is still on. We're still doing our own IP address with SLAAC.
Yes. The device still builds its own IP address, just like before. It still does the DAD check.
Yeah.
But now that O flag O for other is switched on.
So the router is saying, build your own house, but come to the front desk to get the phone book.
That's a great way to put it. The router is great at routing, but maybe the network admin wants to use specific DNS servers. So the router tells the host, get your IP from me via SLAC, but go ask that DHCP server over there for the DNS info.
And why do we call it stateless?
Because the server isn't keeping track of you, it's just a billboard. It hands out the same DNS information to anyone who asks. It doesn't care who you are or what IP you have. It maintains no state, no list of leases.
When would you use this?
It's common in places like universities. You want students to connect easily with SLAC, but you need them all to use the university's DNS servers to access internal resources. It's the best of both worlds.
Got it. Okay, on to path 3, the control freak. Stateful DHCPv6.
Right, this is for admins who need total control. Here, the flags are M1, the A flag is usually off, and O doesn't really matter.
M for managed.
M for managed. The router basically puts up a stop sign. It says, do not make your own IP, go directly to the server and ask for one.
So the router is just a signpost in this scenario.
That's all it is, a gateway. The host sends a request out, and the server does everything. It provides the full 128-bit address, the DNS servers, the domain name, the whole package.
And since it's stateful, the server is writing all this down.
Oh yeah, it keeps a detailed lease database. It knows your PC has this specific address, and it knows that lease expires in exactly 24 hours. This is what you see in banks, government, high-security networks. Total accountability.
So what about that relay agent I saw mentioned in the infrastructure section? If the server is in a different building, how does my request even get there?
That's a classic networking problem. That initial request from your computer is a multicast message, right? And multicast doesn't normally cross routers. So if your DHCP server is 5 network hops away in a data center, it's never going to hear you.
So the router has to act like a messenger.
Exactly. You configure the router as a relay agent. It listens for those local multicast help me messages, packages them up into a normal unicast packet, and forwards them directly to the server's IP address. It's the bridge.
So we've got these 3 paths, DIY, hybrid, and managed. How do we, as users or admins, know which one is actually happening?
You have to check reality. On a router, a command like show IPv6 interface is your best friend. It'll show you if the flags are set and which multicast groups it's part of.
And on the server?
You check the bindings. Show IPv6 DHCP binding. If it's stateful, you'll see a list of leases. If it's stateless, that list will be empty because, it's not tracking anything.
And for a regular person on their Windows machine?
Good old ipconfig all. It will actually tell you if DHCPv6 is enabled and show you the DHCP server's address if you're in a managed environment.
So to tie this all together, we've moved from just plugging in a cable to navigating this really complex logic tree.
And what it shows is that IPv6 was designed from the ground up for flexibility. It knows that a coffee shop network is totally different from a corporate headquarters.
And the beauty is in the choice provided by those flags.
Exactly. Those 3 little bits, A, O, and M, let an administrator, tune the network to be exactly as hands-off or as controlling as they need it to be.
It's just amazing that all of this happens in the blink of an eye. You go from existence with a link local address to connectivity with a global address, and you never see a thing.
All without clicking a single button.
Before we wrap, I want to circle back to something you mentioned earlier, the privacy aspect.
Right. This raises a really interesting question for all of us.
We talked about EUI64, that method where your hardware's unique serial number gets baked right into your public IP address.
Yeah, we talked about the tracking. But think bigger for a second. With IPv6, we have enough addresses to give one to every single grain of sand on Earth. We could have given every device a permanent, static address for life. It would have been simple.
But instead, we chose chaos.
We chose chaos.
Yeah.
We chose to have our devices generate random numbers every time they connect just to stay anonymous. We literally engineered privacy back into a system that was originally almost too transparent.
It's a fascinating trade-off. In a world with trillions of addresses, is anonymity the default setting? Or is it something we actively have to build and fight for?
That's the question. Sometimes just being lost in the crowd, or in this case, lost in a sea of random numbers, is the only way to stay safe.
Something to think about the next time that little connected icon pops up. Well, that's it for this deep dive. Thanks for listening.
See you in the next one.